Okay, welcome back to the third part of the introduction lecture to density functional theory, and now we will talk a bit about the electron density. So the wave function, as we used it in the previous part, includes all the electronic states of our system. And it's quite important to understand that the wave function is not an observable. So we can't measure the wave function, which becomes quite problematic if we want to compare it to experiment. And also something we need to take into account, that electrons are indistinguishable. What it means is, if we have, for example, one green electron and we change the position, the probability, right, it's here, we square over the absolute value of the wave function, does not change. But what that means is that the probability, however, is physical interpretable, so we can actually put some physical meaning into the probability. Going one step further, if we think about electrons, those are fermions with a spin of ½ So the wave function must be antisymmetric if we change an electron position, like the green one again, right? We change the green one from first to the third one, so we get the minus sign, right? We did that for the probability as well, but because we take the absolute value and square it, the minus anyhow does vanish. However, if we don't take the probability, we need to make sure that because of the spin ½ it becomes antisymmetric. What it basically means is the antisymmetric principle is, it's more like the quantum implementation of Pauli's exchange principle, right? We can't have two electrons occupying the same state. So that's impossible. We can't have two electrons, right? We cannot have two electrons with a spin up. We can't do that. It's always spin up and then spin down. And further, what we learn from the probability is that integrating over the probability, right, to find an electron in a given space is 1. So if we have our core and then the electron circles the core, finding the electron within a closed circle, a closed sphere, needs to be 1. And now we can use that to do the step to the electronic density. Basically, right, because the probability to find an electron in a given space equals to 1 leads us directly to the electronic density, which is basically the same impression, right? We integrate over all the electrons and all the states, and that's basically our electronic density. And it's quite important to understand that the electronic density is an non-negative function. That first of all means that at the infinite space of an atom, right, if our atom is that one, so our atom, and the electron circles the nuclei, finding it here needs to be basically finding it at the infinite distance from its main location needs to be 0, and integrating over the density equals to the number of electrons. And it's quite important here to understand that unlike the wave function, the electronic density is an observable, which we can actually measure with experimental methods like X-ray diffraction. So it provides us with a method or with a solution to actually compare to experimental measurements, whereas the wave function does not. So making the step from the wave function towards electronic density makes actually sense because we get a comparable variable. How does the electronic density look like more in practice? Let's take water, for example. Right, and we have our oxygen here and the 2 hydrogen here and here. And as you can imagine, we have 2 lone pairs here, by the way. In the water molecule, the oxygen takes more or less the electrons from both hydrogens. So finding an electron, the probability to finding an electron near the oxygen, is way larger than at the hydrogen positions, and that's actually what the left-hand plot shows here, right? We see still, sure, there's some electronic density here and here at the hydrogen places, but the majority of electrons is located at the oxygen position. First of all, because we have the 2 lone pairs, and then we get also the shared electrons from the hydrogen. What you also see quite often in literature is that people plot the isosurface around a molecule, for example. What it basically means is that we set a minimum threshold for the density, and then we can plot it. So obviously it's surrounded near the molecule, and then it becomes, because we cut it off at further distances. It's a bit similar to the left-hand plot, but the right-hand representation is way more common, and then sometimes you could also color it if you take the potential also further into account. And then what you would see is that here the areas around the hydrogen are less electronegative, because electron density from the hydrogen is moved towards oxygen. So you would see that the area around the oxygen has more density than the hydrogen area. And that's how the electronic density becomes quite an important value in quantum mechanics, especially then in density functional theory, and that's the physical meaning. So it actually has a physical meaning, and we can represent its physical meaning by plotting it. And now we understood where the electronic density comes from, and in the next 2 lectures we will learn how to use it to solve the Schrödinger equation.